Welcome back. This is week 9 of Graduate Statistics, University of Cincinnati. And here we are to provide you with a formal introduction to analysis of variance to answer the question that we have at hand, which is vocabulary scores, knowledge about vocabulary knowledge, different across different social classes? That's the answer. That's the question we're trying to answer. And we went in and selected ANOVA to investigate and answer this question because we're talking about differences between means. So we have a numerical variable. We are talking about differences between more than two means. So t-tests are out. So we're with ANOVAs. And we checked to see if the assumptions of ANOVA were met, and they were met. So we will move on and actually understand what the analysis does. So ANOVA, analysis of variance, comes from the fact that ANOVA deals with variability. It partitions variability into two types, which I alluded to before, which is the between group variability and the within group variability. So we can think of variability, the total variability bucket, as the full spread of the data, right? Because imagine if you take the whole data in terms of vocabulary score here for all of the four groups. We took the mean, the overall mean, the universal mean across all of the four groups. There is an overall mean, right? And if we get the deviance of every single score from that mean, it's telling us how much variation I have to explain because the mean is not sufficient. If there was no variation across the mean, then the mean itself, the overall mean, would be a good model for our data, right? If the groups were all the same, if the people's vocabulary score were pretty much all the same with very little variation, then if we use the mean to model vocabulary score, the overall mean across all of social classes would be a good model for the data, right? But the more variation around that mean, that overall mean the scores have, the more room I have to bring in other factors to explain that variation, right? Why am I having so much spread around the mean? What can explain that, right? So we have this total variability bucket. And then within that total variability bucket, I want to ask, is there some of that variability attributable to social class? On the background, on the mathematical background, what I'm asking is, would it be useful to model this data with more than one mean? Would it be useful to have 4 different means? And it would only be useful to have 4 different means if the mean of each group deviates considerably from the overall mean, right? Because if I take the overall mean and the means of all of the groups are very close to that mean, then one mean might be good enough. But if I have the means for the different groups being far away from the mean, from the overall mean, right? One group is above the overall mean, the other group is below the overall mean, one group is a lot above the overall mean, the other group is just a little bit. So then it's telling me that the variability attributed to class or the variability attributed to group is pretty high, right? And if it's high enough compared to variability left over, variability that's not explained by the groups, then if this one is big enough, then our F ratio will be high because remember, F ratio is the ratio between between group variability and within group variability. Of course, here, because of our example, we have variability attributed to class because we have 4 different means expressing the means for the different social classes, and variability that I can't explain because I don't have other types of means in my data, other types of independent variables or explanatory variables in my data, only class. So the leftover, if I compute this one, the total minus this one is the leftover, is what I can't explain with my particular explanatory variable. All right? So generalizing here, when I say variability attributed to class, you can think variability attributed to whatever explanatory variable or group that you have in your data set. And vocabulary score here, you can generalize to whatever response variable that you're dealing with on your data set. All right, so that's the logic of ANOVA. So here's our data structure. You have your numeric variable. So you see how this is the long format. You have the numeric variable here, which is the score in the vocabulary test. And we have the class variable that identifies which group that score came from. The ANOVA output would look something like this. If we want to know the effective group, which in this case is class, we would have to look at the probability of finding the particular F ratio that we computed under the null hypothesis. And here, because the p-value is less than 0.05, we would reject the null hypothesis that all the means of vocabulary scores for all of the groups is the same. But now let's dive into this table step by step. Let's start with this piece, the sums of squares. Remember I said we have a bucket of overall variability to be explained, and that's your total variability. So total reflects numerically the size of the bucket that we start with to explain, all right? So this is this variable here. It's telling us the size of that circle. Now, how do we compute that? It measures the total variability, and it's calculated very similarly to variance, except we don't divide by sample size in the end, right? What we do, we get the mean, the overall mean of all vocabulary scores that is included in every single group. We compute the mean, the overall mean, and we get the square deviation of each score from that mean, and we sum it. That's this value here, okay? So here's the formula. We have, this is the overall mean, the grand mean of the response variable. Why are we calling the grand mean? To differentiate from the group mean. The grand mean is the mean across all of the groups. You get the scores of every single participant, and you get the grand mean. Sum them, divide by the number of participants, you get this one. Then you get every single value of vocabulary score of every single participant, and you subtract from the mean, you square it, and you sum. So it's almost like variance, but it's just summing the squares. It's not dividing by the number of scores. So it's not variance, it is sums of squares, because you're summing the squared deviation, okay? So to do that, just so we make it super clear, the SST, in our case, the grand mean is 6.14. That's the mean of all means. And then the first score, this is not a place to be. The first score is 6. So I subtract 6 from 6.14 and I square it. Then the next score, 9. I subtract it from 6.14 and I square it. What's the next score? 6. So on and so forth. And I sum them all. And this would be the value that goes on the table that we talked about. The value that will represent the total variability bucket. So this is done. We understand how we get that one. So this is how total is the total bucket of variability, and you understand, how to compute it. I'm so sorry for me today. Okay. Now let's learn how to compute the between group variability, the sum of squares of groups. So it measures the variability between the groups. Explained variability. That's the variability that we are explaining using the different means that I can compute from the different groups. That's why we call it. That's the variability that we're able to explain. This is the total variability to be explained, and this is the amount that I can explain if instead of using one mean, I use 4 means in this case. So it's square deviation of group means, the group means that I have, from the overall mean, and it's weighed by sample size. So here's the calculation. Here I have the number of observations in each group, because if they vary, you need to multiply by the numbers that you're using to actually compute the deviation. Here is the grand mean again, And here, instead of using the individual observations, I'm using the mean of the group. So here, let's say it's the mean of the lower class, okay? And this is the grand mean. I compute the difference and I square. You want those to be large if your explanatory variable is gonna do some work. If these deviations are small, if every single group mean is very, very, very close to the overall mean, it's telling us that they are going to do pretty much no work in explaining the variability bucket to be explained. So let's see how this is calculated. Again, we're weighing by the number of people in the group. So lower class has 41. So it's 41, that's the one, times the overall mean, you subtract from it the mean for that group, and then you square it. Then you do the same for the working class. We have 407 people that said they were working class. So again, you take the group mean and you subtract from the overall mean. You do the same for the other groups, sum them all, and that's the variance that we can explain using the means. So roughly 7.6% of SST, the sums of squares total. So we know how to compute now variability attributed to class or attributed to group more generally. How about the sums of squares of error? So we have the total variability to be explained. We have the variability that can be explained with the explanatory variable that we have at hand. And what's left over is just this minus this. It's the total minus the variability that can be explained, the between group variability, okay? Are we good? So just the difference. Measures, so sum of squares error measures the variability within the groups, the variability that happens regardless of whether you are in group A or B or C. So it's unexplained variability. It's variability that has nothing to do with the fact that you are in class A, B, C, or D. And the computation is pretty easy. It's just, you have the total, you have what you can explain, and you have the unexplained by the factor that you have in your data set, which here is just class. So one minus the other, that's where this number comes from. All right, so that's variability attributed to other factors. Now, what's the mean squared? Well, this, as you saw, we just summed the variability and we didn't correct by anything. It's absolute values. We didn't average at all. So we need to average. And that's what we do with the mean squared error. So this is just the overall total square error, and we need the mean squared error. So we need a way to get from these measures of total variability to go from the measures of total variability to average variability. And we need to scale by a measure that incorporates sample sizes and number of groups, which is the degrees of freedom. And it kind of makes sense that, for instance, for the sums of squares related to group, that I am going to use the number of groups. It's related, I have to scale by the number of groups I use to compute deviations. The total squares, I used many more scores to compute my deviation. So I have to, it's expected that it will be bigger because I'm just summing all of them. So I need to weigh by that. So when we come back, we'll learn how to compute the degrees of freedom that then will come in to transform these total sums of squares to some average deviation that can then be compared. See you soon.